So we're going to be going through an exam review for all the topics in AP Physics 1. And so we're going to start here with kinematics. General structure of the review is I'm going to focus on derivations symbolically, as well as all the key problem solving skills and things like that. We'll go through a couple of equivalent to the qualitative, quantitative translations. They have some derivations and things like there that'll be really useful for you because most of the FRQs involve derivations. So first thing is just remember on kinematic side of things is that we apply the kinematic equations. These are only applicable. These four kinematic equations are only applicable if the acceleration is constant. If the acceleration is not constant, we're not allowed to use these equations. It's only when A is constant. Cannot emphasize that enough because a lot of the tough parts of AP Physics is not just the equations, not just about equations and plugging in numbers, but it is about what it is when the equations apply, when you're allowed to use them, and what situations. Near the surface of the Earth, the acceleration is downward at 9.8 meters per second squared. Couple of facts: maximum height, we have a vertical velocity of 0. That's because it's no longer going up. When you transition from going up to going down, you change the sign or change the direction of the motion. That is when the velocity is going to be 0. At rest, or if it's dropped or released, we also have a velocity of 0, and then constant speed has an acceleration of 0. And so remember, the problem-solving steps for this is really to list out, we'll talk about the problem-solving steps below, but we're going to list out the variables, the 5 kinematic variables, identify which 3 variables are known or unknown, and then solve for the last unknown. So we're going to go through that process. Graphs of motion, you always want, when you're looking at graphs, multiple choice for response, you always want to think about what the y value is, what the slope is, and what the area represents, okay? So when you have a position versus time, the slope is the velocity, slope of velocity versus time is the acceleration, the area under velocity versus time is the displacement, and the area under the acceleration versus time is the change in the velocity. So this is change in. So there's kind of this relationship between area and slopes, but you always want to remember what these 3 things represent when you're looking at a graph of anything, not just for kinematics, but for other problems. Projectile motion. That's where we have vectors. We may decompose into the x and y components. So remember, in projectile motion, we decompose vectors to be the x and the y direction. T is the only common variable between the x and y, and at maximum height, again, the vertical component of the velocity is 0. Make sure we're consistent with the signs. And here is our problem-solving steps that we want to focus on. We're going to list all 5 kinematic variables for the x and y directions. We're going to assign which way is positive and negative. We're also going to remember that in free fall, that the acceleration is downward at 9.8 and the horizontal acceleration is 0. We're going to decompose velocities, all the vectors into x and y components, identify the unknowns of what you're trying to solve for, and then choose the appropriate kinematic equation based on the quantities you know. Okay? And last part, this is kind of a little bit new or a little bit more in depth for AP Physics 1 for you guys in 2025 or later, is the relative motion. When 2 objects move in the same direction, you subtract their velocity vectors to determine the displacement and the velocity vectors to determine the relative motion, or from their perspective. And when we're moving in opposite directions, so if I'm having a car heading towards you, if a car is going east at 30 miles an hour and another car is coming towards at 30 miles an hour, it looks like from this guy, he's coming closer at 60 miles an hour. Opposite directions, we're going to add those velocities to get the relative motion. When they're going in the same direction, right? So if both cars are moving to the right at 30 miles an hour, it looks like neither of them are moving relative to each other. Okay, so we subtract their velocity vectors when they're moving in the same direction, add them when they're in opposite directions. So let's take a look at a few graph problems, some multiple choice, and then free response questions to just understand how those concepts kind of come together. At time t equals 0, cars moving in the positive direction along a straight road. The graph represents the car's velocity as a function of time. Okay, so that means the y value is the velocity. The slope is the change in the velocity over the time, change in the y variable, the change in the x variable, that is the acceleration, and the area is the y variable times the change in the x variable, that is the displacement. Okay, so those are the things we know. So always start with that when you have a graph. So at time t equals 0, it's moving in the positive direction on a straight road. The graph represents car's velocity as a function of time. Car's position at t equals 0 is x equals 0. The position of the car times 1 second, 2 seconds, 3 seconds are x1, x2, x3 respectively, which correctly ranks their position That's the position, not the displacement, from greatest to least. Okay, so the area is going to give us the change in the position. So in the 1 second, if we look at the area here, that is the change in the displacement. That's going to be x1 minus where we started, which is 0. So that's just x1, right? So that area here represents x1. Now the next area from here to here, what does this area represent? This is x2 minus x1. It is the area between times 1 and 2. That is that area is going to be the displacement. Now that's positive area, so that means x2, it's moved further to the right compared to x1. So x2 is definitely greater than x1 because this area is positive. And then last here, the area from 2 to 3, that area is the displacement. That is literally x3 minus x2, position at 3 minus position at 2. That is greater than 0 because that area is above the x-axis. It's positive area. So that means x3 is greater than x2. So therefore, we're just, and another way to think about it is the velocity. The y value is positive the whole time. He's moving to the right. So that means he's just going to keep getting further and further and further along. So it's going to be x3 is greater than x2 is greater than x1. All right, we have a similar one, same problem, but the y value, again, being the velocity, the slope, like we said before, is the area, is the acceleration, and the area is going to be the displacement. Now, they're asking you which could represent the acceleration of the car. That means the slope needs to represent the acceleration. So over here, the y value equals the acceleration. So any slope that you see here has to match the y value down here. So here the slope is 0. So from here to here, the a is 0 because the slope is 0. Horizontal lines have a slope of 0. So I should expect to see 0 acceleration, a y value of 0. It's that there, and there are correct, but this one, the y value is non-zero, so it can't be that one. Okay, next, the slopes are now negative, right? So a negative slope means I should have a negative y value down here because that's a negative slope. It's down and to the right, negative slope, so I should have a negative. So that one's negative, that one's negative. Look at this one. It's negative but slightly negative. So that part's okay. However, look at the transition. This is more negative, less negative, less negative. So I should have a more negative y value followed by a less negative y value down here. Here the y values are constantly negative, but the slope is clearly changing as it's moving. So it can't be that one. This one, the y value is slightly negative, and over here the y value is very negative, but we should expect the slopes to shrink, get closer to 0 as we move along, so it's not that one. That's why this is going to be our correct answer here. Okay, let's look at a derivation problem. We have a truck of mass m moves to the right with a constant velocity vt on a horizontal road. Projectile of mass m is launched vertically from the bed of the truck with an initial speed v0 relative to the truck. Air resistance is negligible. From the perspective of the observer on the ground, describe the trajectory of the projectile. Would the projectile land back in the truck, land behind it, or land in front of it? Justify your answer. So we're ignoring air resistance. It's normally what we default to do. So in this case, what's going to happen is he's going to go up. Now, again, when this is a relative motion. So from the perspective of the truck, it's like he's just going to go straight up because right now what's happening is the projectile, the mass here m, on this truck is moving to the right vt, and the truck is moving to the vt, but relative to the truck, it looks like it doesn't have any horizontal velocity because you would just subtract them because they're both moving together to the right. Okay, so from the truck's perspective, he's just going to go up and then come back down. Right? He's going to launch up and come back down. However, he has a rightward component. So as he moves along, it's going to go up. So as far as the truck, it's going to land back on the truck, but the truck's going to move to the right, and this thing is going to come up and then come down and land right on where the truck is over here in the same spot. So from the truck's perspective, it's going to go up and down. Okay? But from the outsider's perspective, it's going to be a parabolic path. So it is describe the trajectory. It's going to be moving. It's going to be a parabolic path to the right. And it would land, and it lands on the truck. And why does it land on the truck? Because they both have the same horizontal velocity. Because they have the same horizontal velocity. because neither of them are going to have any acceleration in the x direction, right? Because he's moving at a constant speed here, and there's no, again, ignoring air resistance, there is no acceleration in the x direction. Remember, in two-dimensional motion, when we're in the air, the acceleration is only downward at g, or 9.8. Same horizontal velocity. Okay, derive an equation for the projectile's horizontal displacement as a function of time in terms of Vt, V0, and physical constants. Okay, so this is projectile motion. We are going to list out our x and y variables, V0, V, A, T. These are our 5 kinematic variables we list out. That's kind of always our process. And we're going to assign direction, so we're going to say right is positive. We see we've drawn the motion. That's an important part. Okay, so the displacement vector, the displacement vector of the box is going to be this way. So let's talk about the initial velocity. This is supposed to be relative to the ground. So horizontal displacement is what we would like to know. The initial velocity in the x direction is Vt, because it is moving with the truck. It does have an horizontal velocity. The acceleration is 0. The vertical displacement, because the displacement vector is only to the right, the vertical displacement is 0. Okay. The initial velocity in the y direction, let's say up is positive, then is V0. Final velocity, don't know, but the acceleration is downward at g, so that's going to be negative g. And then the time is the shared between them, same time between them. Now, I don't necessarily know the time. What variables do I know? I know this one, this one, this one, and this one, and this one. This one, I have 3 known quantities, and remember our kinematic equations work is if you know 3 quantities, you can solve for the 4th unknown quantity. So what kinematic equation relates those 4 variables? It's going to be V0t plus 1/2 at squared. That's going to be 0 is equal to V0t minus 1/2 gt squared, because this acceleration is negative because it was pointing down. You can factor out a t because it's equal to 0. So that means t is equal to 0, which doesn't seem valid, or the V0 minus 1/2 gt is equal to 0. And here, if you solve for t, you're going to get 2V0 over g, right? So move it over, times 2 divided by g. That's going to be our time. That time gets to come over here. And so now I have the time. I have one more piece of information. So then I can use the same equation in the x direction, because these are my 3 known quantities and my 1 unknown. So you're going to have delta x is going to be Vt times the time, which is 2V0 over g. Okay. Now, this 1/2 at squared terms, because the a is 0, if I plug it into there, that's just going to be 0. So this is it. So it's just going to be Vt times 2V0 over g. That is going to be the equation for the horizontal displacement. Does your equation from part B support your reasoning from part A? Okay, justify why or why not. So is he going to travel the same distance in the same amount of time? Well, let's think about the truck. The truck will travel velocity truck times the time, and that time is going to be here. It's Vt times 2V0 over g. So yes, because the truck will travel the same horizontal distance in the same amount of time, in that time, then yes, because the truck, will have the same velocity Vt in the same time. So in the same time, the time being 2V0 over g, it covers the same distance. And that's what we mean to catch it. It means that in the same time, the truck's gonna be in the same spot where the box is gonna be, or the mass is gonna be, and so thus it's gonna land on the truck. It covers the same distance. Okay, that's how I would answer that question there. Okay, let's take a look at this. Car mass m is initially at rest at a stoplight. When the light turns green, so draw the motion. We have a velocity, car at rest. When a car turns green, it accelerates forward with a constant acceleration a1 until another time t1. So this is t equals t1 here. After reaching that certain speed, the driver takes his foot off the gas and the car slows down due to a constant acceleration a2. Now, here he's speeding up. Here the acceleration a2 is going to go this way until he comes to a stop here. Okay, so I've drawn out the motion. Suppose the driver increases acceleration a1 while keeping the acceleration a2 and total distance traveled the same. What is the total time for the car's motion? Increase, decrease, or stay the same? So we're going to keep the deceleration and total distance. We're going to travel the same distance, but we're going to increase the acceleration. Well, the total time, well, it's going to take less time. Hopefully that makes sense. It decreases it because with a greater acceleration, we're going to travel same distance in less amount of time. So a greater acceleration means the car is moving faster and will cover the same distance in less time. Okay. Part B, derive an equation for the total distance traveled in terms of A1, A2. We want to know this distance here in terms of A1, A2, and T1. Okay? That's what we want to know. Now, because the acceleration is not, this is a one-dimensional motion. The car is just accelerating and slowing down. Because, okay, this is super important, because the acceleration is not the same the whole time, we must split it into two separate sets of motion. We got to do this motion when the acceleration is A1, separately from this motion when the acceleration is X2. So let's do the first. So for t less than or equal to t1, let's do the motion. We're going to list out our kinematic variables, and we're going to say right is the positive direction. The displacement is what we would like to know. The initial velocity is 0. The final velocity we don't know, but the acceleration is a1 to the right, which is positive, and then the time is t1. And so what kinematic equation connects those variables is this kinematic equation, v0t plus 1/2 at squared. So that's going to be, the displacement here is going to be 1/2 a1 t1 squared. Okay, so this distance from here to here is 1/2 a1 t1 squared. Okay. Now the second, so from t1 to stop, that second part of that motion, we're again going to list out the kinematic variables. Again, we want to know what the displacement is. The initial velocity, not stated in the problem, final velocity is 0. The acceleration is negative a2 because it's pointing to the left. We said right was positive. And we also don't know the time. Okay, so we don't have enough piece of information. However, because it's the same motion, we know that the velocity here is the same. So the final velocity here is going to match the initial velocity here, because whatever velocity we accelerated to can be used as the initial velocity. And once we know that, then we can derive the displacement over here. Okay, again, thinking about three pieces of known values to find the one unknown value. So here we're going to use v is equal v0 plus at. You can use any equation to find v, but this is probably the easiest one because you have all the information. This is a1 t1. So that means this is a1 t1. And then I don't need to know the time. I need an equation that relates these four variables. And that's going to be the equation v squared equals v naught squared plus 2a delta x. The final velocity is 0. This is a1 t1 squared plus 2 times negative a2 delta x. And you can solve for delta x. It would be a1 squared t1 squared over 2a2, right? That's just a math solving at that point. And so that's the displacement from there to there is going to be a1 1/2 a1 t1 squared over a2, okay, or a1 squared, right? And so then the total displacement is going to be the sum of them. It's going to be 1/2 a1 t1 squared plus 1/2 a1 squared t1 squared over a2, like that. Okay. In another scenario, the driver accelerates less than a1, but for the same time t1. Predict how the distance traveled changes. Okay, so does it increase or decrease? You want to look. This is one of those cases you want to look at the equation we just derived and decide, is it going to go up or go down? So the acceleration for less than a1. So a1 is going to decrease, going to go down, down. Everything else stays the same. Okay. So everything else, they say everything else stays the same. So if a1 goes down like that, then the whole overall it's going to decrease. It's going to decrease because the both terms added together in part B will decrease with a smaller a1. So this is one where we look at the derivation and then decide what's going to happen at that point.